Okay, so it's 12 o'clock. We'll go ahead and get started. Your test, I'm still working on grading them. I'm halfway done. There's only 26 of you, so I don't really like to farm out tests to a TA. That's why it's a little bit slower. TAs are probably faster than I am. I am aiming to have it done and ready to get back to you on Friday. That's even more likely if kind of tomorrow turns into a snow day, so we'll see what happens. But I'm shooting to get them all done for Friday. And then of course there's another test next Friday, so kind of on Friday I should be able to tell you more about that, and the next test will be our last test, finally. So before we get started, are there any questions about anything? Yep.
I couldn't find when the final is.
It's something weird about that final schedule. If you go to the registrar's office webpage, like there's a link to look at all final exams, and our Physics 2055 final exam is there. It should also be on the MUN Physics homepage, so if you Google MUN Physics undergraduate final exam, it should take you right there. Does anybody know off the top of their head?
It's like the 14th, 3 to 6, or something like that. 13th
Yeah.
or 14th.
Okay, so have a look. If you can't find it, send me an email and I'll send you the link to the webpage. I just hesitate to say what I think it is out loud because I'm afraid I'll be wrong, and I just don't want to commit. Better if you look it up on the official website, but if you can't find it, let me know. So I'll ask for your feedback a little bit. The first 3 tests we sort of had in class and you kind of didn't get any notes. The last test was the full class and you were allowed to take the sheet of notes. Which format did you like better? Or you don't know till you get the grade back? The second way a little better. Nods for agreement. Okay, so if there was a little bit more liking of that format, I was inclined to do the next test in that format, so probably that's what we're going to roll over again. So that means you would be allowed a sheet of notes in the next test coming up as well, so if you want to keep working on that as we lead into the test, you're more than welcome to. Okay, nothing else. So last day, we kind of finished up talking about magnetic force on a moving charge. Today we're going to roll into the fact that moving charge, that's just another way of saying current. So that's where we're going to get to today. So we said that we know, and this is an experimentally observed result, that if you have a charge moving with velocity v, and we place it in a magnetic field B, then it's going to feel a magnetic force, FB equals QV cross B. Okay, so we've established that. It's well known. You can measure it, easy to find. So let's take this idea of the fact that charge is moving around and ask ourselves what's current. Well, current is the flow of charge over time. When we defined our current, whichever symbols we used, it was charge divided by time. I'll write Q over little delta T there. So let's take this idea and think about this down here. So in our equation, we have Q. If our charge moves some amount delta S in a time delta T, that would be the velocity. Okay, so it moves some small amount of position delta S. That'll be a vector because it has a direction, and it takes a time delta T. Then that's our velocity. We cross that with the magnetic field B, and we take a look at what we have here. In this expression, we've got a Q divided by a delta T. That's current. So this bit right here, why don't we add a note there just so we know where it comes from. So our charge Q moves some displacement delta S in some amount of time delta T. Therefore, V equals delta S over delta T. Okay, that should look nicer in your notes. So let's just rewrite this equation once more. So Q over delta T, that's current. We can say that delta S is the length of the conductor that the current flows along. You might call that length a capital L. The diagram here has a lowercase l. You could see uppercase or lowercase, it doesn't matter, just remember that L stands for the length of the conductor. I, L, cross. When we defined current, we said it has a direction. The direction is the direction of flow of positive charge. Here, I'm putting my vector symbol on top of the L, right? The L, we say, has the same direction as current flow. So whichever way current flows, that's the direction we take our L to be. So really here in this equation, we just write, and this is more historical than anything else, the magnitude of current times the vector L, where the direction of L is the same as the direction of I. You could also write L times I cross B, you'd get the same answer, okay? But this is kind of historically what we see. So I and L, same direction. So this tells us that if we have a current carrying wire and we set it in a magnetic field, it will feel a magnetic force. And this was the basis of that DC motor lab that you did in Physics 1051. You put that current carrying wire near a magnet and it spun around because it felt a magnetic force. Okay, let's see. So if our force is IL cross B, we can always do the math. So if we know the vectors, we can do it out with the cross product, or we can do magnitude and direction. The magnitude of the magnetic force would be the magnitude of the current times the magnitude of the length times the magnitude of the magnetic field times sine theta. Careful with your theta here. This is the angle between L and B. If you want to calculate the magnitude, then you'll use your right-hand rule to find the direction. So just like all the right-hand rules, your thumb goes in the direction of the first vector, so that's your I or your L. Your magnetic field, your second vector, goes with your index finger, and your extended middle finger is your result or your magnetic force. So the right-hand rules always work that way. Something cross something equals something. Okay, questions? So this was basically just a repeat of F equals QV cross B. Why don't we go straight ahead and do an example? I got a little thread or something on my mask and it's making my nose really itchy. I'm really sorry to be scratching, but I just can't think straight. So in our example, we've got a little circuit set up. We've got a 15-volt power supply, a 3-ohm resistor in a closed loop. So from our Ohm's law analysis, we know that we hook this up, current is going to flow, V equals IR, we can calculate the current. We know it's going to come out of the positive end of the battery and flow around the loop this way. We're going to take this current loop and we're going to put the right edge of it in a magnetic field that points into the page. And we're going to ask, what is the net force on this circuit? So we have a current carrying wire, we're putting it in a magnetic field, and we want to find the total force. So there's our goal. So why don't we start with figuring out our magnetic field. So the current is going to flow out of our 15-volt battery, out of the positive terminal, coming around the wire this way, around the wire this way, out this way. So there's our current I. Ohm's law says V equals I times R. I equals V divided by R. 15 volts divided by 3 ohms equals 5 amps. Okay, so the current flowing around that circuit is 5 amps. We want to figure out the net force on the loop. So let's think about what we know about the net force. So if we're calculating the magnetic force, we know that magnetic force, FB, equals current times length crossed with the magnetic field. The direction of the length matters, right? So, and length and current are in the same direction. So if we look at our loop, on the top part, the length or current points right. On this bit, the length or current points down. And on this bit, the length or current points left. we kind of have three different segments here. We'll have to find the force on each bit and add them up to get the total force. So it's like we have three lengths of wire. So let's do them one at a time. Our first length is from here to here. There's our L1. The next length comes down like this. That's L2. And the next length comes over like this. This is L3. So everybody good with the three L's? Let's put our coordinate system in there, X, Y, and Z. So let's think about each of those forces. We'll try using the equation, and then we'll back up the directions with our right-hand rule. This one's going to be pretty straightforward to do our direction. So the force on the first segment, force magnetic 1 equals current times length 1 crossed with the magnetic field B. So we get current, our length has a length of L1 in the X direction. You might notice that we don't know how long that length is. Is it 1 centimeters, 3 centimeters, 10 centimeters? Who knows, right? It doesn't say. So I'm just going to call it L1. It points to the right, so I'm going to say L1 times I hat. That's going to get crossed with our magnetic field, which points into the page. So that's a negative J direction, negative K direction, sorry. So I've got I times L1 times B times negative I cross K. Everybody good with that step? Negative I cross K, so we'd like to figure out what that is. So I cross K is negative J, negative I cross K is plus J. If we were going magnitude and direction, then the magnitude of the force would be I times L1 times B times sine of 90 degrees, because the two things are perpendicular. The direction, your thumb goes with your L, your finger goes with your magnetic field, your extended middle finger shows the force that points straight up. So that vector looks like this. So we'll use the right hand. Okay, either way is fine. They're both correct, whichever way you prefer to think about it. So there's our force on the first segment. Let's do the force on the next segment. So segment 2, FB2 equals current times L2 crossed with B. Current L2 is coming down, so it's minus L2J hat, crossed with my magnetic field, which is minus B times K hat, equals I times L2 times B, J cross K. J cross K is I hat, I L2 B I hat. So that tells us that the magnetic force points to the right. If you prefer your right hand rule, we can absolutely do this. We have to put our thumb in the direction of L2. One thing I can do is turn my arm around like this. An easier thing I can do is turn my paper around like this. Okay. So if you're having trouble with your right hand rule, don't be afraid to twist your piece of paper around. So L cross B gives me my force. So my right hand rule backs up the direction for that force. So magnitude and direction, FB2 equals I L2 B sine of 90 degrees I hat. The current was 5 amps. L2 is from here to here. Our picture shows us, so that's 10 centimeters. B is 50 milliteslas. 50 times 10 to the minus 3 teslas. Sine of 90 is 1. That's going to be in the I direction. 0. newtons I hat. Okay, and remember, I couldn't figure out FB1 because I didn't know L1. Okay, I've got 2 of them done. Let's do the third. So for my third one, I think I'm going to skip the math way. I'm going to go right to the right-hand rule way. FB3, the magnitude is I times L3 times sine 90 degrees. To get my direction, put my thumb in the direction of L3, so my thumb is going this way, my finger goes into the page, my extended middle finger points down. Okay, so L is my thumb, B is my finger, force is my middle finger. So this direction is down, that's my F3. So that's negative J hat minus IL3, oops, I dropped my B, sorry, times B J hat. Okay, so far so good? We're taking our time with this one just to make sure we're kind of good with all the steps. So those are my individual 3 forces. We're not asked for each individual force, we're asked for the net force. So for our net force, we have to take the sum of all of them. So my net force is FB1 plus FB2 plus FB3. Of course, you can't forget that they're vectors. If we look at our diagram and our equations, so our diagram has this much in on top, this much in on bottom. The length of L1 and L3 are the same. So from our diagram, we can see that the magnitude of L1 equals the magnitude of L3. If that's true, then the magnitudes of these forces have to be the same, and they're opposite directions. So I've got minus or plus I L1B J hat plus 0.025 newtons I hat minus I L1B J hat equals 0.025 newtons I hat. So FB1 and FB2, B3 are equal and opposite. So those two, the top and bottom ones, they cancel out. Okay, any questions? Pretty straightforward. Okay, let's do something that has a little bit more meat to it. So for our next one, the magnetic field is uniform. It points out of the page. So that's all of our little dots there pointing outwards. So this is our magnetic field B. The conductor is a semicircle with radius r that's shown in the picture. The conductor carries a current I. I haven't drawn the current on the picture, so I'll go ahead and put that in now. So I'm going to say my current flows from the left towards the right, staying on the arc, of course. So there's my current I. Find the total magnetic force on this piece of wire. Okay, so we want the magnetic force on this bit. We know it's going to feel a force because it's a current carrying wire set in a magnetic field. This one is harder though, because when we try to do IL cross B, L is not a single direction. We've got a loop here. So let's try and get through this part. FB equals IL cross B, not simple. So when we have something with this weird sort of a shape, what we do is we pick a small piece of our wire. So let's pick a small segment. We'll say that that has length DL. This little length DL is a small current carrying wire in a magnetic field. It's going to feel a small force. We can find the direction of that force with the right-hand rule. So L is this way, force is out of the page, magnetic field is out of the page. So my L is this way, field is out of the page. My force is pointing in towards the center of this loop. So this little piece of current feels a little magnetic force. that points towards the center. This little magnetic force we call dF. Then to find the net magnetic force, we have to add all those little bits up. So this is similar to what we did with electric fields. We found a little bit of field due to a little bit of charge. We found the net field by doing the integral or summing them all up. We're going to do the same deal here. So a little bit of force, dFB, is made on that little bit of wire, I times dl cross B. Okay, so we're still good here, where the direction is identified from using the right-hand rule. If we want to find our net force, FB, we have to sum up the whole thing, dFB. And by sum up, we mean do the integral. There are two strategies to go from here. You can do this as an integral. It certainly works, but it's a little bit tricky because your length is a little bit funny. So either you have to go to some kind of cylindrical coordinates, which you're probably maybe not familiar with, or you have to break this length into I and J components, recognizing that it changes as you go around the circle. That's fine, you certainly can do it, and I have done it and worked through it. Or we can go magnitude and direction. Magnitude and direction, I think, is the most straightforward, and we'll just have to rely on a little bit of symmetry to give us our final answer for direction in the end. So let's start attacking this with magnitude and direction. So the magnitude of the net force is going to be the integral of the magnitudes of all the little individual forces added up. So we're just going to go magnitudes. So this is going to be the integral of the magnitude of IL cross B. And we already said that that was I times the magnitude of L. Oh, sorry, there should be DL. I times the magnitude of DL times the magnitude of B times the sine of the angle between DL and B. So are we good to hear? So I just put in what the magnitude was. So let's figure out something for this DL first. So DL is a little bit along the circle. DL is an arc length because it's a little piece along the circle. So there's our DL. And from a high school geometry class, maybe you remember that DL, or the total arc length, would be r times theta. So a small bit of arc length would be r times d theta. So a little bit of arc length is r times d theta, where r is the radius of your circle, and theta is your angle in here. Okay, so we can put that in our expression. So we've got the integral of I times r times d theta times b times sine theta. So this is the magnitude of my force. I'm getting closer. I'm probably seeing that I'm set up to do an integral with respect to theta. This is not hard. I've just got a sine theta in here. I'm going to take my constants out front of my integral. So I, r, and b are all constant. Integral of sine theta d theta. Now we want to think about the limits of the integral. Just like when we did electric fields, to find the net electric field, you integrated from one end of the rod to the other. Same deal here. We'll integrate from one end of our loop to the other end, from one end of the segment to the other. At the first bit of our segment, theta equals 0. So theta is 0 at the beginning. At the other end of our segment, theta is a half of a circle, or pi radians. So there's the limits of our integral. The integral of sine theta, I don't know that I would give you that integral on a test. I probably think you know power law and you know the integral of sine and cosine. So those straightforward ones, I expect you to remember those. Integral of sine is minus cosine. That's got to be evaluated at pi and theta. So I've got I times r times b outside of minus the cosine of pi minus the cosine of 0. Cosine of pi is minus 1. Minus times minus gives us a plus, cosine of 0 is 1. So minus of minus 1 is 1, 1 plus 1 is 2. So our magnitude of our net force FB is 2 times R times B. So there's the magnitude of the force. This one wasn't too painful of an integral. To think about the direction, let's see. When our DL is over here on this side, the magnetic force points down and to the right. So let's ask if there's any symmetry that could help us find the direction of the net force. So anytime we're over here on this side, the magnitude of that force, we'll do our right-hand rule, always points down and right. Okay, so no matter where I picked it, our DF would point towards the center. If I come over on this side, I'm going to draw a DL over on this side, and I'm going to try and get it at a point symmetric to where I drew it the first time. So here's a DL coming this way. If I use my right-hand rule to do my force here, my length goes this way, my magnetic field is out of the page, my force is towards the center of the circle. So over here on this side, my magnetic force points down and left. This would be true no matter where we picked our DLs. If I picked a DL right here, and I picked its twin over here, this one is down and right, this one is down and left. If I picked them up here, down and right, down and left, the left and right stuff cancel. Okay, so due to the symmetry, everything on this side is down and left. Everything on this side, oh wait, sorry, I got a whole left right thing. Everything on this side is down and right. Everything on this side is down and left. The left and right business add up to be 0. Okay, and the net magnetic force ends up pointing down. So then we would put in minus J hat for our direction. And then the horizontal cancels due to symmetry. And then we toss in the fact that we use the right-hand rule as well. Okay, any questions? An extension of something this you could try is what if you had like the whole circle of the loop? What would be the total magnetic force? Maybe that would be something to try. If you really like doing cross products, you could give it a go, not using the right-hand rule. You might find it a challenge, you might find it fun. Yep.
If cos of pi and cos of 0 are both negative 1, 1, wouldn't it be 0 and then IRB?
Yeah, you can be so careful with the negative signs here, right? So our integral is negative cosine. So for my first term, I've got negative cosine of pi. Cosine of pi is negative 1.
Oh.
Negative of negative 1 is 1, right? Those signs, they'll get you every time. Yeah. Okay, so let's keep going. For a homework example, I've got these straight segments again. It's not very different from what we did with the circuit. So I'll leave that one for a homework and I'll post the answers. You just do ILB for each one and add them all up. So now let's come back to here. And then this is coming back a little bit to what you did in that motor lab in physics 1051. So if we ask what happens to a current carrying loop in a magnetic field, I played the video last time, and we saw that it spun around, and that's definitely true. I'm sure you made that for yourselves. And when I played the video and I brought one in to show, I said it was the orientation of the loop was really important. Here's where we're going back to why the orientation of the loop was important. So here's what's going to explain why that matters. So let's think about a loop. I could do a circle. I preferred to do a square. So you can do a square motor just like you could do a round motor. The square is just going to be easier to look at. So let's think about the forces on each side of this loop. Let's find the net force, and then let's think about the motion. Okay, so we've got our current loop, we're going to find the force, and we're going to think about the motion. I'm gonna say that my current comes up counterclockwise. So there's my current going through this loop. I'm gonna say that my loop has a length L in this direction. And let's find the force on each of the 4 segments. So we'll use the idea that F equals IL cross B. L and B are perpendicular or parallel everywhere. So if we have an angle, it's just going to be 90 degrees. So we'll do magnitude and direction just to find each of our forces. So let's go with this segment first. So our length is going with the direction of our current, so up this way. Our magnetic field is pointing this way, so there's our finger. The direction of the force is our middle finger is into the page. So right here on this part of the loop, the magnetic force is into the page. Here's our FB. And the magnitude of that force is I times L times B times the sine of 90 degrees or 1. Everybody good with that segment? We'll come to the top part of the loop. Our current is to the left. Our magnetic field is to the right. We're taking the cross product of 2 things that are anti-parallel. That gives us 0. Okay, so when they're parallel or anti-parallel, there's no force. So on this top segment, the force is 0. Then we come to this segment. Let's find the direction of the force here. So L comes this way, B comes this way. Magnetic force is out of the page or towards us. So the force over here on this bit is a dot in a circle. Magnetic force FB is I times L times B times sine of 90 degrees. Then on our bottom segment, our current is to the right, our field is to the right, the force is equal to 0. So there's the net force on that current loop. Everybody okay with each of the segments? So for our net force, we've got 0 and 0, they don't do anything. We've got an ILB into the page and an ILB out of the page. So what's the net force going to be? 0, right? So these 2 are equal in magnitude, opposite in direction. So net force equals 0. If the net force is 0, remember Newton's second law, force equals mass times acceleration, means the acceleration is 0. So that's an interesting result. Acceleration equals 0. Sometimes that throws people for a loop. So our loop is definitely spinning around in a circle. It's definitely moving, but the acceleration is 0. So at first thought, it might seem like those 2 thoughts can't go together. How can something move and have an acceleration of 0? Well, the deal is that this loop does not go from here to here. We say that it doesn't have any translation. When we talk about F equals ma and we find the acceleration, we're always talking about the acceleration of the center of mass. We're treating it like a point object. So it's 100% true that while this loop does move, it doesn't actually go anywhere. The center of mass doesn't move. It always stays dead at the center. So if acceleration is 0, it means there's no translation. It definitely has motion, however, and the motion is that it rotates. So this part of the loop feels a force going into the page. This part of the loop feels a force coming out of the page, and that makes it spin in this direction. So it spins like this. If it spins, that tells us that the net torque is not 0. So there's a rotation about the center axis, about center. So the net torque is not 0. So here's where we start talking about torque on current loops. leave that there for a second. So we're good to here. So the net torque is not zero, so let's start to think about the torque. So if we want to think about the torque, I definitely want to get a look at what's happening. So I'm going to pretend I'm looking from the bottom of the loop. So I'm just looking at this bottom end on this side, so my eyeball is down here. There's my eye looking up. So on this side, the current is coming towards me, so that's this part. On this side, the current is going away from me, and the magnetic field still points this way. So this is my view from the bottom of the loop. So my force here, when I'm looking this way, points up. So there's my magnetic force here. And my magnetic force over here points down. And then here is my center of my loop right here. The center of my loop, I don't know how well you remember your torques from physics 1050. The center of the loop is where it's going to rotate about. That's what we're going to call our pivot. And now we want to ask, since we know the torque is not zero because it is rotating, can we figure out an expression for the torque? We know the torque produces the rotation. So let's start to think about torque. So our definition of torque, and your book kind of goes a slightly different tactic. You're welcome to follow your books, but I'm going to present kind of the way I like it. Torque is R cross F. People mostly remember that. You might have to review it. So you got your distance from the lever arm crossed with the force applied at a point relative to the pivot. So torque is going to be the sum of R cross F. So R is from your pivot to the point of application of your force. So there's the R for that force. Here's the R for this force. And then when our forces are this way, so I've got the sum of R cross. Here's where we remember that F is IL cross B. So I've written down my torque, and I've put in the fact that when I say force, I mean magnetic force, IL cross B. Now the next thing I'm going to do is just move my brackets. So I've got the sum. I'm going to take my current out front because that's just a constant. You can move constants wherever you want. So I comes out front. I've got the sum of R cross L cross B. And instead of having my brackets around L cross B, I put my brackets around R cross L. That's okay to do. It doesn't matter what order you do them in. R cross L, this is an interesting idea. The sum of R cross L, that's the area vector. So that's how you find the area vector of any sort of a loop. So that gives us for our torque, the net torque on an object is the current times the area vector crossed with the magnetic field. So here's an expression to find torque on a current loop. This I times A, that's kind of special, and that's called the magnetic dipole moment. That's got a symbol of mu with an arrow. It's got units of amps times meters squared. I put the word dipole in brackets because sometimes it's magnetic moment, sometimes it's magnetic dipole moment. So dipole might be said, might not be said. So torque equals mu cross B. So to find the net torque on a loop, you take the magnetic moment, you cross it with the field that it's setting in. And overall, this mu value, it describes how a current loop acts like a magnet, right? It describes the magnetic nature of a current loop. Okay, questions? All right. So let's just talk about this mu a little bit more. So everything we did here was if we had one loop of wire. In general, we might have more than one loop of wire, so a magnetic dipole moment would be the number of loops times current times the area. So N stands for number of loops. Magnetic dipole moment. It means that our current loops do act like they have magnetic fields, and we can trace those out. Like here's a picture of some magnetic field lines around a current loop. If you set up a current loop, you put a little compass in, you'd be able to measure those field lines. That's something you can observe. Because area is a vector, it means our magnetic moment is a vector. So those vectors have the same direction. We use a right-hand rule to find the direction, so always with the right-hand rules. So if you have a current loop, in order to find the direction of the area vector or the magnetic moment, you look at the direction of your current. So I've got a tape roll with an arrow, so I'm saying the current comes around this way. You take your right hand and you make a circle with your fingers. You put the circle of your fingers with the direction of the current and you stick your thumb out. That's the direction of the magnetic moment. Okay? So you match your curled fingers to your current loop and your thumb is your magnetic moment. If the current changes direction, then you got to turn your hand over. Your fingers match the current, your thumb goes into the page. So there's our magnetic dipole moment. We said that our torque was mu cross B. So this shows that if our magnetic dipole moment is parallel to our B, the torque is going to be 0, and there's no rotation. If the magnetic moment is perpendicular to the magnetic field, the torque will be a maximum. And things will spin. Okay, so this was why the orientation of that loop was so important. You had to get those two things perpendicular in order to get a torque. When you want to calculate the torque due to a magnetic moment, you can always do the cross product, or you can do magnitude and direction. The size of the torque vector would be mu times B times sine theta. That's the angle between mu and B. And you would use your right-hand rule. So you would do mu cross B gives your torque. Always the same way. Mu cross B is torque. Okay, so let's do a torque example. So in this example, we have a 10-turn loop of wire. So this is telling us that n equals 10 when we're thinking about our magnetic moment. It lies in a horizontal plane. It's parallel to a uniform horizontal magnetic field that's shown in the picture that's just pointing to the right. It carries a 2 amp current. You may or may not notice that the direction of the current is not shown. Okay, we definitely know it's 2 amps. It's either coming this way or the opposite way. The loop is free to rotate about this axle. That's not magnetic, so it's not going to do anything. We hang a 50-gram mass off one edge. What size of a field should we have that would keep that loop from rotating? So there's our question in this problem. If it feels a little bit artificial, I would say, yeah, this is a bit artificial. I don't think this would be a very interesting experiment to do, but there you go. So let's write down the things that we know. N equals 10. Current is 2 amps. No idea about the direction. That hanging mass, I'll call that M, is 0.050 kilograms. We're preventing the loop from rotating. That tells us that the net torque on the loop is equal to 0. So the things that can exert torque on the loop are going to be this hanging mass. That's going to tend to pull it down. And we could also get a magnetic torque. Okay, so these bits of wire will feel magnetic forces. Those forces can cause it to tend to rotate, so we can get the torque, which is mu cross B, due to the magnetic field. So we've got two kinds of torque, the torque due to the hanging mass and the torque due to the magnetic field. They'll sum up to be 0 if this thing is not going to rotate. That tells us that these two torques are equal and opposite. Okay, so far so good. So let's write down the torque due to the hanging mass first. So we know they're going to be opposite direction. The magnitude of the torque due to the hanging mass is going to be the magnitude of R cross F. So that's the old school way to find a torque. R is your vector from your point of rotation to where the force is applied. So there's our R vector. The hanging mass exerts a downward force equal to its weight. So there's the force due to the hanging mass. The angle between those two things is going to be 90 degrees. So I've drawn R, I've drawn F. So I've got R times F times sine of 90. F was a force equal to the magnitude of the weight, so R times M times G. You can either put your numbers in or wait till afterwards. So R is 0.025 meters times my hanging mass, 0.050 kilograms, times G, 9.81 meters per second squared. I did my numbers wrong again. Okay, I'm going to fill that in afterwards. On the absolute worst at a calculator. So my magnetic torque, or did somebody calculate it already? No, okay. So for my magnetic torque, the size of my magnetic torque is the size of the magnetic moment crossed with the magnetic field. So that's going to be mu times B times sine of 90 degrees. So for my magnetic torque, there's two ways it could go. If the current comes around the loop this way, then the magnetic torque is up. If the current comes around the loop that way, the magnetic torque is down. So my magnetic moment is either up or down. My magnetic field is to the right, so the angle between them is 90 degrees. Okay, so whether it's up or down, up and down are both perpendicular to right. So that gives me mu times B. Mu was the number of turns times the current times the area. That's going to be times the magnetic field. So I've got 10 turns times 2 amps. The area is going to be the length of the loop times the width of the loop, 0.1 meters times 0.05 meters times the magnetic field. That magnetic field B is the thing that I don't know. I'm just going to go ahead and calculate that one because I think I would like to have that number. 0.025 times 0.05 times 9.81. 0.0123 newtons times meters. So we know that they have to be equal and opposite. Torque due to the mass is torque due to the magnetic field, 0.0123 newtons times meters, equals 10 times 2 times 0.1 times 0.05, 0.10 amps meters squared times E. Gives us a magnetic field of 0.123 Teslas. Okay, so you can figure out the size of that magnetic field just by figuring out that the torques have to be equal and opposite. To get your direction of the current, I've just got a minute left, so I think we can get that direction of current. So if we look at this length of the wire right here, the hanging mass pulls down, so the magnetic force has to push up. That's the way to get them to be opposite. So the force is up, that's your middle finger. The magnetic field points to the right, that's your index finger. So force is up, magnetic field is to the right. The current has to be coming towards you down the wire this way. So I cross B gives that force. So you can figure out the direction of the current doing this. You could also do it using torque as mu cross B, so that works as well. Okay, that takes us right up to 1250, so we'll quit there. and then we'll probably finish this chapter on Friday.